My name is Mariam Tahan. I'm a Principal Software Engineer in the Office of the CTO on the Emerging Networking Tech team. Today I'm going to talk about how you can migrate a DPDK application from using the DPDK PMD to a standard Linux-based interface that's utilizing AFXDP. Let's look at the what, the why, and the how of what it is we're trying to do. So what is it we're trying to do? We're trying to figure out what in-kernel eBPF networking advancements can I use with my existing DPDK application. Why we might want to do that is for a number of reasons. Firstly, to decouple the app from the underlying infrastructure. We might want to leverage the Linux kernel to deal with non-application traffic. We might want to have some better integration with standard networking tools. We'll be looking for better portability across multiple platforms for a DPDK-based application. And we may want to move from a polling-based model to an event-based one. But one of the key things that we want to be able to do or not do, essentially, is that we don't want to rewrite our DPDK application. So one of the things I would like to highlight before we get into the meats of this demo and presentation is that the goal is for this demo essentially. One of the things that we want to do is dispel the whole FUD around having to rewrite a DPDK application if you want to migrate it to use AFXDP. And the last thing to highlight is that this is not a performance-based demo. It's simply a functional demo. Certainly more time can be spent to try and fine-tune the application or the AFXDP part to figure out, the right number of cores, whether or not to use busy polling, and so on and so forth, if that's something that people are interested in doing. So the application we're going to use for this demo is the OMEC UPF. OMEC is the Open Mobile Evolved Core, and it's part of the Open Networking Foundation. So they have a reference design for a 5G mobile core, and one of the components of that, or the main data plane component, let's say, is the UPF. So the OMEC UPF essentially implements a 5G user plane function that's compliant with the 3GPP standard. It's built on top of the BEST framework, and it supports multiple backends. Through DPDK, it supports PMD and AFXDP. It's important to highlight that AFXDP in this case is the Linux driver that's being used alongside or integrated with DPDK. It also supports the Cloud Native Data Plane CNDP, and its AFXDP IO driver, and it also supports AF packet. So today what we're going to show you is the UPF running with both the DPDK based PMD in Kubernetes, and then we're going to show the UPF running with AFXDP and what change we had to make essentially to transfer the UPF from working with the PMD to working with AFXDP. Okay, so if we start with the UPF running with the DPDK based PMD, what we have as part of this demo is essentially two servers. Server 2 is going to be running a DPDK based packet generator that's also using BEST, and this is going to be running in a Docker container. DPDK is going to bind two PFs directly to it, and it's going to drive the traffic over these interfaces. On server 1, we're actually going to have a single node Kubernetes cluster. On this cluster, we are going to use the SROV device plugin essentially to collect and advertise our PF resources to the kubelet. We're going to have Multis running on this node, and we're also going to have two CNIs, Flannel and Host device, to bind our PFs to the UPF pod. Now, it's important to note that there was a couple of limitations on this server that I was using. No VTT was enabled, and I had no IO MMU either supported on the platform. So I couldn't use like VFs for DPDK. I essentially had to use the PF, and that's why I couldn't use the SRO VCNI and had to use the host device CNI to get things up and running. Obviously, when we have DPDK running in the in the BES container in the UPF pod, the interfaces are going to be bound directly to DPDK in user space. There's a bunch of other containers that run as part of the overall UPF pod, a root kettle or a root control container, PFCP container, another container that essentially allows us to access the does a bit of port forwarding, allows us to access a nice visual representation of the UPF pipeline. And this roots container runs at the start to install some essential routes and things that we need essentially beyond the capabilities of the host device CNI to allow us to be able to run DPDK based UPF. Okay, so let's go ahead and run the UPF on server 1 with the DPDK based backend. So we have a YAML based pod spec that's actually quite large. I can show it here. But essentially, this is describing two network attachment definitions, one for the access network, another for the core interface network, and they have they have different subnets allocated to each. Then comes in our actual pod specification itself. It's requesting, an interface from each of the different networks. It has an init container that is the roots container that we spoke about. It sets up a bunch of different interfaces. Then we actually get into the real containers that are part of the BES-based UPF, I guess. The root kettle container, the main container, which is called BESD. We can see the two interfaces being added to there. It is a privileged container, unfortunately, because I am using these PFs. It makes the situation rather difficult. Whereas with VFs, you potentially run your container with much more limited capabilities. And the last container is a PFCP container that's going to program all the various rules, PDRs, FARs, QERs, etc. into the UPF so we can forward traffic. Okay, so let's go ahead and create that container, or that pod even. Okay, so the various containers should be up and running at this stage. So if we just check out the logs for the BESD container. Yeah, that's up and running. Okay, so what we, just to showcase that is indeed up and running, let's forward the port locally to my host machine here and check out that we can actually see the pipeline up and running. Yeah, so we can forward, or we can zoom out for a second. This is the BES pipeline and it's up and running at this stage. There's the PDR lookup table, QER, FAR lookup, and so on. all the way through. Okay, so let's go ahead and install the different rules through the PFCP agent, and then run some traffic. Okay. So this command will just simulate the creation of the various different rules through the PFCP container into the main best container. It actually takes a little bit of time to run, but we can actually see it installing the different rules or updating. Here, for example, you can see the number of rules being inserted in the PDR lookup table, same in the QER lookup table. And it just takes a little bit of time to finish up. Okay, so now the full complement of rules have been installed. Let's go ahead and pass some traffic through the UPF from the Docker container running the package in. Okay, so if we jump back to our pipeline, we can see there's a number of packets. There's at least 1.7 million packets per second passing through the different parts of the pipeline. And if we, hey folks, so when I originally recorded this demo, the traffic for the OMEC UPF based on DPDK was being directed to a bad route sync. So I've just fixed that up here to show folks what happens when it's going to the right route sync. And so we can see 1.6 million packets per second coming in on the interface. And this time we can see things going through the PDR, QER, and FAR lookups as we expect. And on the slice meter, you know, traffic's then being redirected to the FAR execution part of the pipeline, and that's being redirected through the appropriate route at the rate of 1.4 million packets per second. Let's try and run the AFXDP based UPF next, but before we do that, let's talk a little bit about the differences with the interfaces using AFXDP. Okay, so we are going to use the same setup on server 1 as we did for the pure DPDK PMD based demo. We're still going to have Multis, Flannel, and host device CNI. We're going to use the SROV device plugin to pick up and advertise the different PFs to kubelet, and the CNIs will plumb them then into the UPF pod. So the first major difference that we're going to notice here is the fact that the driver used is going to be the Linux-based driver. An XAP program is going to be installed on each one of the netdevs that we are attaching to the UPF. This XDP program is going to filter only application traffic to the best container, and all other traffic will essentially be processed by the kernel. DPDK will use AFXDP sockets that are attached to the Linux-based netdevs, and it will process traffic through those in user space. So let's go ahead and get that running. Okay, so let's go ahead and create the AFXDP based pod. Again, we have a pod spec similar to that as that we had for the DPDK based PMD. So let's just go ahead and create that pod. And everything should be up and running. So if we do some port forwarding, sorry, everything is now up and running. So if we do some port forwarding and jump back to our pipeline, yeah, the pipeline is up and running. So again, let's go ahead and install the PFCP rules. And this will take some time, but we can see them again updating as they did with the DPDK based configuration. And while those rules continue to install, let's just have a quick look at the main difference in configuration around the two UPFs. So the main configuration files for the two UPFs is a JSON based configuration, and in it you're able to select the mode that you want things to work in. So you can select the DPDK based mode, and that's what we did for the previous part of the demo. And for this this AFXDP based demo using DPDK, we're selecting the AFXDP mode. And the only major difference from the application point of view is that when we run with AFXDP mode, we essentially pass in this additional argument to the EAL init DPDK function, and it's a VDEV argument that specifies that we want an AFXDP based device or interface or AFXDP based socket, if you like, on a specific interface, and we give it a start queue number and then the number of queues that we wanted to configure. In our case, we were only configuring one queue to process the GTP traffic. And then on the DPDK based mode, we just don't pass this VDEV argument at all to the EAL init function with DPDK. So we didn't actually have to change any part of the application itself to be able to change the backend from a fully DPDK based PMD running in user space to AFXDP using the Linux Kernel Driver, and leveraging the kernel-based driver with our DPDK application. So let's jump back and check on these rules. Still installing, so we'll give it another few seconds or minutes. Okay, so now the rules are fully installed. Let's go ahead and pass traffic through that pod in the same way we pass traffic through the DPDK PMD based pod. And so we can see some traffic starting to travel through the pipeline here, coming in at 1.4 million packets per second, traversing the PDR lookup table, QER lookups, FAR lookups, and also being output at 1.3 million packets per second. And that's the interface completely transitioned to using Linux-based AFXDP. To provision the pods, we had to obviously unbind our interfaces from DPDK, and then provision the pod. And other than that, we just had to set up some basic routes and various filters to just make sure that the traffic coming up into the UPF application is GTP paced traffic, and nothing else really. And that was the main difference to transition our application from a DPDK based PMD to AFXDP. There's one important thing to note as part of the demo here as well. Right now, there's no VF Linux-based driver that supports XDP, but the future isn't based on VFs with AFXDP. The future is based on sub-functions. And what we'd like to see is essentially our PF being partitioned into a number of sub-functions. Each sub-function will be represented by a netdev in the Linux kernel, and essentially those functions, so exactly the number of netdevs or sub-functions that we need, or queues that we need, will be allocated to our application, allowing us to much better partition our NICs or provision our NICs to exactly what each application needs without any waste. And that's really it from the demo point of view. Thank you very much for your time.